Hi everyone. Here in this video, we would like to derive an expression for surface tension. Before going ahead and talking about the derivation of that, let me define surface tension once again for you. It is defined as the force acting per unit length tangentially on an imaginary line drawn to the surface of the liquid on both sides, normal to the imaginary. Right? If you have not got the definition properly, please go back to the first or the second video of the playlist of the surface tension so that I have discussed in detail about the definition and meaning of surface tension. Here, let me go and talk about expression for surface tension. To derive that expression, let me consider the capillary tube. As I told you earlier, capillary tube is a tube having thin radius, small radius when compared with the length of that tube. It's like a small tube having very small thickness, very small gap, fine bore in between the walls. I have drawn little big only to demonstrate, but practically it's not this big, right? Imagine this capillary tube is now placed vertically in a vessel which is filled with liquid. Is filled with liquid. The surface of the liquid is not going to be flat like this. Assuming adhesive forces are dominating, it's having a concave shape. Here, if you want to remember back what do you mean by angle of contact that I have done in the previous video, this point is called point of contact. At this point of contact, I shall draw two tangents. One tangent drawn to the liquid surface. Liquid is concave, therefore surface is the tangent is gone in touching with that. One more tangent is drawn to the wall of that capillary tube, but into the liquid. This is how I have to draw. There is an angle between these two, and this is angle of. In this angle of contact, in this example I have taken, generally this happens in many cases. Angle of contact is less than 90. Adhesive forces, that is the force of attraction between the molecules of the liquid and capillary tube are dominating than the coercive forces, that is the force of attraction between the molecules of that liquid or water. Thus, there will be a capillary rise, liquid level rises in the capillary tube up to a certain height. Let us say that height value is equal to h. Let that height is equal to h. You may understand it? That height is measured from the liquid surface, not from the bottom of the vessel. Now, here also the liquid acquires the same concave surface because of the property of surface tension. I can repeat the discussion that I have made in the above case. What is that? This is a point of contact. To know the angle of contact, I shall draw two tangents. One tangent drawn to the liquid surface this way. One more tangent drawn to the wall of the capillary tube into the liquid. Between them there is an angle theta, and that angle is called angle of contact. And what's the direction of the surface tension at this point? This is tangentially in this way. That's the direction of surface tension. Being this angle is theta, this angle is also theta as per the basic mathematics. Now, I can resolve this surface tension into components. Components as what? Adjacent to theta, that is t cos theta. I will rather say resolving t. I will talk about the definition of the surface tension. Let me come here first. Surface tension is defined as force acting per unit length. So, in this case, the part of the surface tension acting or causing this capillarity is only t cos theta. Look at this. That is t cos theta. That is t sin theta. Look at this t sin theta. What it is trying to do? It is trying to pull the liquid in this direction, but that is against the wall of this capillary tube. That's the sin theta is trying to break the wall and pull the liquid along the sides, which is not at all possible. Therefore, it's not going to do anything useful. But look at this t sin theta and cos theta. That is trying to pull the liquid upward, and that is successful. So the part of the t, what I need to take into consideration is only t cos theta. Right? What is it force? Force is acting in the upward direction by length of the free surface of the liquid. This liquid is actually having a circular shape. If you see it like this, any of the ball, any of the cylindrical pipe, capillary tube is a cylindrical pipe. The cross section is circular. Look here, this is circular. Therefore, the length of that circular shape is cross section of this length, that is having, assuming that this is having some radius r, then the length of that will become 2 pi r. So the total force that is acting in upward direction is t cos theta and 2 pi r. Because of the surface tension force, this liquid will be keep on moving. What happens parallelly when the liquid is keep on moving upward direction because of the surface tension increase? All the liquid in the capillary tube above the liquid level will have certain weight. That weight start acting in the downward direction. So the liquid will be able to move up until the surface tension force is able to compensate the weight of the liquid, excess weight of the liquid that is there in the capillary tube. So when weight balances surface tension, the liquid stops rising further. So I need to calculate what is the weight of this part, right? So this part of weight I want to calculate. This is what I am trying to shade. This part of the liquid's weight I want to calculate, which is spread at a height h as I have taken earlier, right? Let's take that into consideration and calculate. Force acting downward direction is the weight of liquid that raised excess in capillary tube up to a height h. So force downward is, assuming its mass is m, g. Mass can be written like volume into density. Let me call density as d for a representation. G, let me just scroll up. Volume can be written like area into length of that liquid in the capillary tube, excess length. I have assumed excess length as h, as I told you. Being the cross section is circular for the cylindrical pipe, area is pi r square, where r is the radius of that pipe. This is all the force acting in downward direction. So the liquid will rise, keep on rising until the F upward is balanced by F downward, right? So what happens? At equilibrium, liquid stops further rising, where force acting upward due to the surface tension is balanced with force acting downward due to the weight of the liquid in that capillary tube. I have already calculated force acting upward directional value. How much is that? As I am showing here, t cos theta into 2 pi r. Calculated the force already acting in the downward direction, pi r square hdg. So pi's can be cancelled, 1 r can be cancelled. What is remaining there? T cos theta into 2 equal to HRdG. Therefore, if we have to write an equation for surface tension can be written like HRdG by 2 cos theta. This is the expression of the surface tension when the liquid has risen to a height h in the capillary tube. In this, what is this each term? Let me just once again tell you. T is the surface tension of the liquid. H is the height to which the liquid raised in the capillary tube above the normal liquid level. R is the radius of that capillary tube. D is the density of the liquid that was taken in. G is the acceleration due to gravity. Theta is the angle of contact. 2 is a number, right? So, but if we are sometimes or many times in generally when we are handling problems, when we are solving problems, as I told you earlier, between pure water and pure glass, means the capillary tube is made up of pure glass and the liquid taken is pure water. Angle of contact is 0. That implies cos theta is cos 0, that is equal to 1. Then this equation can be further simplified as T equal to HRDZ by 2. Be careful, this is valid only when you are handling about pure water and um, pure glass. Many times in a problem, nobody gives what is the value of angle of contact. Maybe it's like ordinary water, it could have been taken like 8 degree as I told. So cos 8 value is a bit difficult to calculate. So many times while people solving these problems, take this thing for granted like angle of contact is 0. Therefore, calculation will be simplified. Just take a note of it, right? So from this, if you write equations further, I just want to spend one more minute for these applications. For this, I can write a formula. Yeah, for pure water and glass, theta equal to 0, T equal to, as I told you, HRDZ by 2. That implies H equation is 2T by RDZ. Or for a given liquid, if you assume surface tension is constant, density is constant, G is constant, 2 is of course constant, H is inversely proportional to R. This H and R are inversely proportional. That's a simple basic understanding too. What does it mean? If the capillary tube is thin, having a lesser radius, capillary rise will be more. If the capillary tube is thick and having a bigger radius, the liquid is unable to rise to that of the previous height. So capillary height, how much it rises simply depends on what is the radius of the capillary tube is inversely proportional to each other, right? This is how I can explain the basic definition of a surface tension, right? And we can derive an equation for the surface tension.